Welcome friends, Igor is here, and in this video we will talk about applying linear algebra to Markov chains. Let's get started. Suppose that on a certain tropical island the weather is stable enough so that we can estimate the weather tomorrow given the weather today. For simplicity, we're going to assume that on any given day the weather can be in two possible states. It could be sunny or it could be raining. We also know if it is sunny today, then with 80% chance it is going to be sunny tomorrow, and if it rains today, then with 40% chance it is going to rain tomorrow. We can represent these so-called state transition probabilities using the following diagram. In particular, if it is sunny today, then with 20% chance it is going to rain tomorrow, and if it rains today, then with 60% chance it is going to be sunny tomorrow. This is an example of a Markov chain because the state of the system at the next step depends only on the current state of the system. We can only estimate the probability of any kind of weather occurring at any day, so the expected weather on any given day can be recorded using the so-called state vector. In our example, the first component will correspond to the probability of the sunny day, and the second component corresponds to the probability of having a rainy day. Let's assume that we arrive to the island on a sunny day. That means for us, the initial state of the system is given by the vector 1, 0. Suppose we are going to stay on this island for a while, and the question is this: can we predict how many sunny days we should expect in the long run? Well, let's do some explicit computation to take a look at the next couple of days. Today is the sunny day, therefore tomorrow we're going to have a sunny day with probability 0.8 and a rainy day with probability 0.2. Next, let's estimate the probabilities for the day after tomorrow. If it is sunny tomorrow, then it is going to be sunny the day after tomorrow with the probability 0.8. And if it is rainy tomorrow, then it is going to be sunny the day after tomorrow with the probability 0.6. But we know the probabilities of tomorrow being either sunny or rainy, so we can compute the probability of the day after tomorrow being a sunny day. A similar argument applies for the probability of the day after tomorrow being a rainy day. If tomorrow is a sunny day, which happens with probability 0.8, then the day after tomorrow is going to be the rainy day with probability 0.2. And if tomorrow is a rainy day, which happens with probability 0.2, then the day after tomorrow is going to be rainy with probability 0.4. So we explicitly computed the state vectors for 1 day after we arrived to the island and 2 days after we arrived to the island. In fact, this computation was linear in nature. Let me explain why it can be represented using the matrix vector product. Let P be the 2x2 matrix called the transition matrix. In this matrix, the columns correspond to today and rows correspond to tomorrow. The first column of this matrix contains transition probabilities if today is sunny, and the second column of this matrix contains transition probabilities if today is a rainy day. The first row of this matrix contains the transition probabilities into the sunny day, and the second row of this matrix contains transition probabilities into the rainy day. Also, let Wk denote the state vector of the system after k days. Then you can see that the state vector of the system 1 day after our arrival can be obtained by multiplying the initial state vector on the left by the transition matrix P. Similarly, the state vector W2 can be obtained by multiplying the previous state vector W1 on the left by the transition matrix P. Recalling that the state vector W1 is equal to P times vector W0, we see that the state vector W2 is equal to P squared times the vector W0. And now it is easy to see the pattern that the state vector at step k is the kth power of P multiplied by the initial state vector. We're interested in the long-term behavior of this system, so let's see what we can figure out. Let's set some terminology. A probability vector has non-negative components that add up to 1. For example, the state vector of our system W2 is a probability vector. The first component of this vector corresponds to the probability of the second day after our arrival being a sunny day, and the second component corresponds to the probability of the second day after our arrival being a rainy day. Each component represents a certain probability, and they add up to 1 because the second day after our arrival is going to be either a sunny day or a rainy day. A stochastic matrix is a square matrix whose columns are probability vectors. For example, the transition matrix P for our system is a stochastic matrix. Each of the columns of this matrix is a probability vector. Let's make one general observation. 1 is always an eigenvalue of any stochastic matrix. Here is a justification of this claim. Suppose we have a stochastic matrix P. This means its columns add up to 1. Let's take the transpose of this matrix P, then the rows of the transpose will add up to 1. Let's take a vector x, all of whose components are equal to 1, and we are going to look at the matrix vector product, P transpose times vector x. Notice that the rows of the matrix P transpose are the columns of the original matrix P. We apply the definition of the matrix vector product, and you see that each entry in this vector is in fact the sum of the entries of one of the columns of the original matrix P. We assumed that all columns of P add up to 1, and therefore we see that P transpose multiplied by vector x is equal to the vector x, which is the same as the scalar multiple of the vector x by scalar 1. This shows that the vector x is an eigenvector of the matrix P transpose, which corresponds to the eigenvalue 1. But in one of the earlier videos, we proved that a matrix and its transpose have identical eigenvalues because they have the same characteristic polynomial. In particular, it follows that 1 is also an eigenvalue of the matrix P. Each eigenvalue comes with eigenvectors. In fact, among all possible eigenvectors of the matrix P which correspond to the eigenvalue 1, it is possible to choose a probability vector. This is not terribly difficult to prove, but it is outside the scope of this video. Such a probability vector corresponds to one of the possible states of the system, and it is called a steady state vector. This is because if the Markov chain reaches this state, it will forever remain in this state. Going from this state to the next state is equivalent to multiplying this vector on the left by the matrix P, but this multiplication does not change the vector W. Let's find a steady state vector for the weather example. We have this transition probability matrix P, which is a stochastic matrix, and we can compute its characteristic polynomial. We see that indeed 1 is an eigenvalue of this matrix. To find the eigenvectors corresponding to this eigenvalue, we consider the matrix P minus 1 times identity matrix. We find the reduced row echelon form of this matrix, and the eigenspace of the matrix P corresponding to the eigenvalue 1 is the null space of this matrix. From the reduced row echelon form, we see that we have one free variable, and therefore the null space can be described as a span of a single non-zero vector. You may want to check out this video, which explains how to find the basis for the null space. But now, among all the possible eigenvectors, we need to find the one that is also a probability vector. Every eigenvector of the matrix P corresponding to the eigenvalue 1 is a non-zero scalar multiple of the basis vector 3, 1. So we just need to scale this basis vector appropriately to get a vector whose components add up to 1. This vector W is the steady state vector for the Markov chain in the weather model. So if our weather model Markov chain with the given transition matrix P reaches the steady state W with components 0.75 and 0.25, then it will stay in this state forever, because W is an eigenvector of the matrix P with the eigenvalue 1. But what remains unclear is this. Can this Markov chain reach this steady state from any initial state? Let me illustrate that not every Markov chain can actually reach its steady state. Let's consider a Markov chain with the following transition matrix T, and it is easy to compute the steady state vector of this system. However, every odd power of T is T itself, but every even power of T is the identity matrix. Therefore, this Markov chain will alternate between two different states unless the initial state is the given steady state. However, there is one condition that is sufficient to guarantee that the Markov chain converges to its steady state from any initial state. A stochastic matrix is called regular if at least one of its positive integral powers contains only the positive entries. And if the transition matrix of a Markov chain is regular, then this Markov chain will always converge to its steady state from any initial state. Again, this is not terribly difficult to prove, but it is outside the scope of this video. Going back to the weather example, the transition matrix P is a regular matrix because the matrix itself already contains only positive entries. Therefore, this Markov chain is guaranteed to converge to its steady state from any initial state, and in particular from our initial state 1, 0. But this means that if we stay on this island long enough, then we should expect 3/4 of our days to be sunny. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see more of these videos. As always, I will see you later, infinitely many times. Have a great day.